In this video, we'll be talking about the Fibonacci sequence. The Fibonacci sequence is a sequence that naturally occurs in nature and all over the universe. Let's take a closer look. First, let's draw a table with all of our values, with the left side being the index value and the right side the actual sequence. Now, the first number of the Fibonacci sequence is 0. The second is 1. The third is 1 again. The fourth is 2, and the fifth is 3. This is pretty normal, we're just counting from 1 to 2 to 3. But then we get to the sixth value, 5. Wait, 5? What's going on here? Well, a Fibonacci number is defined as the sum of the first two previous Fibonacci numbers. This explains why we saw 1 twice earlier, because 0 plus 1 is 1. And this now explains why we see 5, because 2 plus 3 is 5. Knowing that, we can carry on to the seventh Fibonacci number, which is 8, because 5 plus 3 equals 8. And the eighth Fibonacci number is 13, because 5 plus 8 equals 13. And the ninth Fibonacci number is 21, because 8 plus 13 equals 21. And the 10th Fibonacci number is 34, because 13 plus 21 equals 34. Well, now that you're familiar with the Fibonacci sequence, we're going to look at a way to visualize it. Next, we're going to look at something called a Fibonacci spiral. This is a series of squares, where each square represents a number in the Fibonacci sequence. Now, the two smallest squares represent the second and third Fibonacci numbers, which is 1, and as the squares get progressively larger, they represent progressively higher Fibonacci numbers in the Fibonacci sequence. Now, here's an odd relation. If you take a line and make it touch the corner of each square, like so, you get this odd pattern. Now, mathematicians have discovered a correlation in this. If you take the side of the largest square and take the side of the second largest square, let's call them A and B, and then add A and B and divide them by A, it approximates the golden ratio, which is 1.618, etc. Now that's pretty cool, but let's look at some examples of the Fibonacci spiral in nature. This is an example of a Fibonacci spiral in a galaxy. This is an example of a Fibonacci spiral in a shell. And this is an example, although difficult to see, of a Fibonacci spiral in the bed of a flower. Now that you're familiar with the Fibonacci sequence, at least visually, we're going to take a look at the more quantitative side, the math side. As I've stated previously, the Fibonacci number is defined as the sum of the first two previous Fibonacci numbers. The recursive definition of this is on your screen. Now let's take an example. Let's let n equal 5 and try to find the fifth Fibonacci number. This simplifies to f of 5 equals f of 4 plus f of 3. That is to say that the fifth Fibonacci number, 3, equals the fourth Fibonacci number, 2, plus the third Fibonacci number, 1. Now, there's a special relationship that Fibonacci numbers have with each other that make them so interesting to mathematicians. Let's take a closer look. If you divide two random subsequent Fibonacci numbers, let's just say f of 7 and f of 6, they equal some value. In this instance, they equal 1.625. Is that familiar? Well, let's have another example. If you divide f of 9 by f of 8, in this instance, they'll equal 1.619. Well, if you haven't guessed it by now, if you take the limit as n approaches infinity of this ratio, it converges to the golden ratio, 1.618. Using this identity, a French mathematician by the name of Jacques-Philippe Marie-Binet derived a formula to find any Fibonacci number within the Fibonacci sequence. This formula is known as Binet's formula. This formula was also derived with the help of famous mathematicians Abraham de Moivre and Daniele Bernoulli. Now, Binet's formula is on your screen now. It's pretty long, but all you have to do is remember that the golden ratio equals 1.618 approximately, and with that, we can move on. Now, assuming that fn is greater than 0, another formula that accurately describes the Fibonacci sequence is the formula on the screen right now. Now, it's very long, and you may be wondering what's so special about this formula in contrast to Binet's. And the answer is that the newest formula on the screen is actually differentiable, where Binet's formula is not differentiable. this means that we can actually graph the Fibonacci sequence. Let's take a closer look. Looking closer at a graph, we see the x-axis, where they're all inputs of natural numbers, because there are no decimals or negative numbers in the Fibonacci sequence, and the y-axis, which represents our output, the Fibonacci numbers. As for the actual line, well, this is it. It's rather anticlimactic, but this is indeed a graph of the Fibonacci sequence. We see our local maximum as fn equals 1 twice per the actual definition of the Fibonacci sequence, and the rest of it just diverges to infinity. Well, that's all I have for you. If you learned something new, please consider subscribing or liking the video, as well as sticking around for mathematical content just like this. I'm DaVinci Math, and thanks for watching.